All right, so we're going to continue looking at Chapter 4. Okay, so Section 4.2, we'll split it into 2 days. One day we're going to look at a certain case of asymptotes that are a little simpler. Tomorrow we'll look at another case that can happen that's a little more complicated to draw. Okay, so one thing we want to keep in mind with asymptotes is that in a rational function, if the numerator and denominator have a common factor, you don't get a vertical asymptote. What do you get instead? Yeah, you get a hole. You get a hole in the graph. And the thing is, you might not notice that when you graph it on the calculator, because the hole is so small, no matter how much you zoom in, you can't see it. All right, so you might have to find that by hand. That's the only way to find a hole, is to use algebra. Okay, so let's graph this on a graphing calculator and see what happens. We've got x minus 1 divided by x minus 1. What value is not in the domain here? Just one number. Yeah. 1. 1 is not in the domain. So now the question would be, okay, if it's not in the domain, does that mean you get an asymptote at 1? Or are you going to get a hole at 1? What's going to happen here? What do you think? Yeah?
I think it's going to be a hole.
A hole. Yeah, it's going to be a hole. So basically, it looks like we're dividing two things that are the same. So when you divide two things that are the same, you get 1. Well, it's almost going to look like the line y equals 1, except there's going to be a hole in it. So let's do x minus 1 divided by x minus 1. So we hit graph. That's from the concentration problem, so it's probably better to do zoom 6 or zoom 7, doesn't really matter. But there's your graph. So it looks like it's a horizontal line at 1. But if I was sketching it by hand, what I would do is put an open circle right there to show that there's a hole in the graph. I can also show you there's a hole because if I try to trace to when x is 1, it doesn't give me a y value. There isn't one. If I try to go to the table and type in 1, it says error. Now I can go very close to it. 1.0001, that's fine. 0.9999, that's fine. I just can't use 1, that one value. Now, if I change the numerator just a little bit, instead of 1, I'm going to make it 1.2. That's enough to mess it up. So now the top and bottom don't have a common factor. And I'm going to get a vertical asymptote. So just by changing that number by 2/10, or even 1/10, okay, anything besides 1, and the graph is going to look totally different. Okay, all of a sudden now you get a vertical asymptote. Okay. Let's look at this one. Okay. What value is not in the domain for this one? But Tori, value is not in the domain here. 1 again. Do you think I'm going to get an asymptote at 1 or a hole? Okay. How come?
Because, like, if you square that,
Not sure. All right. So Tori thinks we're going to get an asymptote. Anyone else think we're going to get an asymptote or a hole, and tell me why one or the other? Yeah.
a hole because x minus 1 is a factor of x minus 1 squared.
Yeah, x minus 1 is a factor of x minus 1 squared. So if you think about it like this, what happens when you divide them? basically you get the graph of y equals x minus 1 to the first power. You subtract your exponents when your bases are the same. So x minus 1 to the first power, that's going to look like a line with a slope of 1, y-intercept at negative 1, except there's going to be a hole. So let's make it x minus 1 squared divided by x minus 1. Okay, so just looking at it, you have no idea there's a hole there. Okay? Just looks like a line with a slope of 1, y-intercept negative 1. If I zoom out a little bit, I can make the tick marks 1 unit each, so it'll look a little more accurate. But if we try to trace to 1, there's no y value. Okay? So another hole in the graph. All right, so point here is just to kind of show you when you get values that are not in the domain, I don't want you to just think right away, oh, must be an asymptote. No, not always. Sometimes it's just a hole. Okay. I know that kind of looks like a filled-in circle, but can't really do much about it. Okay, but it should be an open circle right on the 1. All right, so that kind of hole, okay, the fancy word for that is called a removable discontinuity. Think of having a hole in a graph as it's a small problem, right? Very small. You could easily say, well, that's so small that if we just redefine the function at that one point, we could make it a continuous function. Because remember, these are not continuous. There's holes in them. But it's very small. So all you have to do is say, okay, I want you to use the formula we just had on the other page for every single number except 1. Okay? And if you happen to try to use 1, I just want you to put the y value as 1. Right? I think I wrote that. No. So let's take the formula we just had. So if you wanted to define it as a piecewise function, you could say, use this formula for any number not equal to 1. Okay, so if you're drawing a picture, do that if you're not equal to 1. If you are equal to 1, don't try to use the formula above. Just put 1. Okay? So if x is 1, just make the y value 1. And what that will basically do, by doing this right here, you're basically doing this. You're graphing that single red dot. If x is 1, I'm telling you to make y 1. So put a single dot. And now, between that single dot and the rest of the points, you've made a continuous function. So redefining the function where that particular hole is basically fills in the hole. That's what you're doing. Okay? You're kind of filling in. It fills in the hole. If you had more than one hole, you would need a couple different conditions. You'd have to say, okay, well, if x is 1, make the y value whatever you need to fill in the hole. And then if there's another hole, well, make the y value whatever you need to fill in that hole. Okay? You're just filling in the hole. Okay. Does everyone see how if you drew this, this would now be continuous versus this one is not? So a hole is called a removable discontinuity. If you have an asymptote, that's not as easy to fix. There's no easy way to make that a connected function because the graph has that crazy curve to it. So it's not like you could just fix one little dot and it would make it connect. It's asymptotes you can't really fix. But small holes, you can just redefine the function at that one value. All right, so when we look at problems, they're going to look something like that today. That's kind of the general form. Let me go to the next page for a second so you can see an actual problem with numbers. Okay, something like that. We have a polynomial on the top, polynomial on the bottom. We always write them in descending order. So highest exponent down to lowest and then the constant. And does anyone remember if I cover up the bottom part? Now we just have a polynomial. We don't have a rational function anymore. What term here basically controls what the polynomial is going to look like? Most of the terms don't matter. It's just one of them that really controls everything. Emily? The first one. And it would be the same thing in the bottom. The first one. The term with the highest exponent controls really everything that's going to happen. These other terms, well, they affect little details, like little twists and turns. Okay. But ax to the n, remember we called that an end behavior model. EBM predicts what the function is going to look like if you zoom out enough. Okay. Well, ax to the n is the EBM for the top. Bx to the m is the leading term in the bottom, and that's the end behavior model in the bottom. Well, if you want to get an end behavior model for a rational function, it's pretty easy. You just take the end behavior model in the top and divide by the end behavior model in the bottom. And the reason end behavior is important is because that's where horizontal asymptotes occur. Right? What's happening as you go really far to the end, either on the right or on the left. So the end behavior model is going to be used to get horizontal asymptotes. All right, so when x starts to get really, really big, whether it's positive or negative, it doesn't matter. That's why I put absolute value. So when you start to get a really large value for x, this entire function basically turns into just that. I think if you had something like x squared plus 2 divided by x cubed minus 1. If x is 1 or x is 2 and you plug them in, yeah, you're going to get pretty different answers. But those are small numbers. If x is 1,000,000 or x is 2,000,000, you're pretty much going to get the same answer in that problem right there. Right? It's going to adding plus 2 and minus 1 to numbers that are that big. It doesn't even really make that much of a difference. All right. So again, whether you plug in 2,000,000 for x or 10,000,000 for x, it's going to be the same answer, pretty much. All right. So we're going to start to look at that and try to figure out a horizontal asymptote without even making a picture. Right? And we're going to use what I circled in red. Okay. That's the end behavior model for the rational function. So you'll have numbers in front. In my problem, they're both 1s, so that's not super interesting. But sometimes they might not be 1s. And remember, when you have the same base, you subtract your exponents. So if you had something like x to the 4th over x cubed, and I want to divide them, that's going to be x to the 4 minus 3. And then you divide whatever numbers are in front for coefficients. Okay, so let's take an example and see if we can find the end behavior model for our function. All right, so it says find the EBM. And then after that, we'll do the horizontal asymptotes. Okay, so let's start with the top. Kathleen, what would be the term that would describe the end behavior for the numerator?
2x squared.
Yep. 2x squared divided by. And what would be the term for the denominator that would describe the end behavior? Yeah, okay.
3x cubed.
3x cubed. Now, 2 over 3, that doesn't reduce. If it was like 2 over 4, then I could. But I'll just leave that part as 2/3. X to the, what's going to be my exponent on x if I subtract my exponents? Yep, -1. Now, what does that mean when you have an exponent that's negative? Tells you where the variable should be. Oh, right.
The variable should be to the right more.
As far as left and right, I think I'm okay with that part.
Oh.
It doesn't really tell you left and right. Think of like our fraction. We have, in our fraction, we have a
whole? Well, no, actually, no, never mind. I have no clue.
yeah, sure.
Yeah.
Yeah.
Denominator, right?
Right. Anytime you have a negative exponent, okay, that means your exponent, your variable should be in the bottom. So if you just put it in the bottom, feel like, well, wait, where'd the -1 go? It's right here. But when you put it in the bottom, you don't write it as negative anymore. Okay. So if it was a -2, I would have put 2 over 3x squared. If it was a +2, I would keep the variable in the top. So negative variable bottom, negative exponent, positive exponent on a variable goes in the top. So that is my end behavior model. Now, take the end behavior model and plug in a really big number for x, and that's your horizontal asymptote. Okay, how about, Robin, when we write the equation of a horizontal line, what letter do we always start with? Yep, so y equals. If it was a vertical asymptote, it would be x equals. And if you plug in a really big number for x, what does that fraction become? What does it approach?
0.
Approaches 0. Right? If you plug in like 10,000, you'd have 2 divided by 30,000. Very, very small. So it's approaching 0. You could also think, well, what if you plug in -10,000? Well, that's 2 divided by -30,000. Still very, very, very small, getting close to 0. So there's your horizontal asymptote. In fact, anytime that the degree in the bottom is bigger than the degree in the top, you always end up with a variable in the bottom, which means your horizontal asymptote is always 0. The only time that starts to change is when the exponents are the same, or when the top is bigger. And then when the exponent in the top is bigger, then we can start to get into some weird things. Right? But when the exponent in the bottom is bigger, that's nice. It's always a horizontal asymptote at 0. Always. Okay, let's look at this one. Right, so Joe, what would be my end behavior model for this rational function?
2x to the 4th.
Yep.
3x to the 4th.
So 2x to the 4th over 3x to the 4th. All right. And what's going to happen there? Click. Right. X to the 4th divided by x to the 4th. If you think of it kind of like I said by subtracting them, it's x to the 0 power. Anything to the 0 power is 1. So we just get 2/3 as my end behavior model. There's no variable in it at all. So now, knowing that there's no variable in that, I'm going to ask the question, but it's kind of a weird question. As x gets bigger and bigger and bigger, with what's inside that box, what happens to the number inside the box? Yep.
It stays the same.
It stays at 2/3. Okay. So your horizontal asymptote in this problem is at 2/3. It's still horizontal. It hasn't gotten weird yet. It hasn't gotten like slanted. It hasn't gotten curved. still horizontal, but it's a little more complicated because it's not at 0 anymore. It's at 2/3. So anytime your highest variables are equal, the horizontal asymptote and the end behavior model is right there, 2/3. Right? So if you let x be 1,000,000 and you plugged it into this, you'd get a number very close to 2/3. If you let x be 20,000,000, you'd get a number even closer to 2/3. If you let x equal like 3, you're not going to get anything close to 2/3. Right? Well, it might be kind of close, but not that close. Right? The bigger you make x, the better and better a predictor this number will be of what's going to happen. Okay. So, questions on that? All right. So what we're going to focus on for the rest of today is the kind of problems I just showed you. We're going to sketch graphs when the degree of the numerator is less than or equal to the denominator. When the degree of the numerator is less than, 2 is less than 3, or equal, 4 and 4 are equal. And we'll see how to sketch them. These kind of graphs aren't too bad to sketch, especially once you do all your asymptotes, because your asymptotes kind of give you like regions that you need to draw things in. So that's the first thing you want to do. You always want to sketch your asymptotes. This one, I'll put an asterisk next to it because it's, if applicable, try to find where your graph crosses the x and y axis. It's always a nice point to plot. But not every graph crosses the axis. Think of this graph, okay, the parent function for all rationals. That doesn't cross either axis, ever. So if you try to find an x and a y-intercept there, it's not going to exist. All right, so to find your x-intercept, that's when you plug 0 in for y. And when you want to find your y-intercept, you plug 0 in for x. You'll know, though, if you get a formula that you can't solve, like this one. Well, if you wanted to find the y-intercept, you'd plug 0 in for x. You can't do that. If you plug in 0 for x, you get undefined. So you can't do that. If you plug 0 in for y, you get a problem that's impossible to solve. You're trying to find what number the denominator would have to be to make a fraction equal to 0. Well, a fraction is not equal to 0 unless the numerator is 0. And this numerator is 1. So it's impossible to make a fraction equal to 0 if you have a 1 in the top. Doesn't matter what you put in the bottom. So that's why you couldn't plug in 0 for x or 0 for y and ever find an asymptote in that problem. Okay, so try to find intercepts if we can. Next, find your vertical asymptotes. That's the zeros of the denominator as long as what? Yep.
They're not that.
Right, there's no common factors. Otherwise, then you get a hole. So find your vertical asymptotes. Find your horizontal asymptotes using the end behavior model. And then once we have our vertical asymptotes, we're going to check the behavior on each side of it. So let's say there's a vertical asymptote at 2. We're going to use the calculator to check not what happens at 2, because 2 is going to give you an error, but like 2.001. It's either going to be up really, really high or down really low. And then you check the other side. So if you check 2.001, check 1.99. And you're going to be up very high or very low. It's always what happens near a vertical asymptote. We just have to figure out, is it high or low? That's where the table comes in handy. And then we can double check our sketch by looking at a graphing calculator. So the first time you sketch one of these, it's going to look a little different. It's not going to look like kinds of things you're used to graphing. But once you know what they look like, in the case where the numerator degree is less than the denominator, they all kind of look the same. Unless you change something or throw something crazy in there. But They all kind of have a similar look to them. Okay, so let's see if we can sketch that by hand. Okay, I like to do the end behavior horizontal and vertical asymptotes first. I'll check the x and y intercepts after. But let's do the asymptotes first. So let's start with our vertical asymptotes. How do you find vertical asymptotes? Yeah.
What makes the denominator 0?
That's what makes the denominator 0. Now, what would make that denominator a little easier to work with if we did want to it? Yeah? Factor it. Perfect. So we're going to factor it. Usually if I'm giving you a problem like this, it's already complicated enough. I'm going to give you one that factors, not one you'd have to use quadratic formula on. So we got x minus 3, x plus 2. Let's double check it. X squared plus 2x minus 3x. Yeah, looks good. So my vertical asymptotes, I have 2 of them. It's when x equals what and what? What are the zeros of the denominator? Yep. 3 and negative 2. Okay, so I'm going to stop for a second, put those on the graph. 3, negative 2. So 1 dotted lines at 3 and negative 2. That's close enough. So 3 and negative 2. Let's do horizontal asymptotes. So to get that, we'll do the end behavior model. Okay. How would I write my end behavior model here? It would be what over what. And for that, it helps to look back at the original problem, not the factored form. Factored form is good for some things. It's not good for other things. Yeah?
X over x to the second.
X over x to the second, which reduces to
X0 over, or no, negative x.
yeah.
1 over x.
Yeah, you can think of it as x to the negative 1, which I think is where you were trying to go with that. So if you think of that as a 1, it's x to the negative 1. But we want to think, okay, negative exponent means it should be in the bottom of a fraction. So it's 1 over x. What happens to that fraction as you let x get really big? What does that fraction approach? Oh. Yeah, it approaches 0. 1 divided by a huge number, very small number. So there is your horizontal asymptote, y equals 0. So let's put that in. Okay, so now I got that. So now I have these regions. I have 6 regions. We usually end up drawing a certain pattern, which I'm going to show you next. All right, so we've got these. 5 we just do last. Let's check the behavior near the vertical asymptotes. So for that, I want to plug in numbers near 3 on each side of it and near negative 2 on each side of it. I could do it by hand, but the table is a lot faster. So we've got x minus 1 divided by x squared minus x minus 6. All right, so what's a number that's very close to, let's start with negative 2, but just to the left of negative 2. Very, very, very close to it, but just a little to the left. Yep?
Negative like 2.009.
Yeah, negative 2.0001. Well, if you plug in negative 2.0001, it says you're at negative 6,000. So when you're just to the left of that green dotted line, you are way, way down. Okay? I can't go to negative 6,000, but just you're pretty far down. Now, what would be a number that's just to the right of negative 2? Yeah.
Or negative.
Yeah, negative 1.99. Okay, we're way up. I mean, if you want to go even more, you could go 999. But hopefully you're getting the idea. You're way up at 600. Okay? So when you go just to the right, all of a sudden, way up there. All right, let's do the same thing with the asymptote of 3. Let's check 2.999. I'm way down. Okay, negative infinity. Way down. And let's check just after 3. I'm way up. I'm up at 400. So these are all points when I start making my graph that I'm going to draw through. All right. And we know we have a horizontal asymptote at 0. Okay. Let's see if we can find intercepts here. Okay. Let's see if we can find a y-intercept. Let's start with that. So y-intercept, that one's easier. You just plug in 0 for x. If I plug in 0 for x, what does my numerator become? Chris? Yep, negative 1. Divided by. And what if I plug in 0 in the bottom for x? What do I get? Yep.
Negative 6.
Negative 6. So my y-intercept is 1/6. So this graph is going to cross the y-axis right about there. Okay. X-intercept. Let's see what that is. So x-intercept is when you plug 0 in for y. The only way you could make a fraction equal to 0 is if the numerator is 0. What would make the numerator 0 here? Yeah, 1. So my x-intercept would be 1. The only thing I have to check is make sure, well, is 1 even a number you can plug in? Yeah, it is. You can't plug in 3 and you can't plug in negative 2. 1 is fine. So this is going to cross the x-axis at 1. All right, so let's draw the middle section because we got enough points there. I think we can do it. So what's going to happen is it's going to curve through this section, and as you head further and further to the left, it can't cross that dotted line. It's got to stay in that section, but it has to head towards that dot. So it's going to have to curve up because it wants to try to cross the green dotted line, and then think of that dotted line, it's pushing it away. It can't. It tries to, but it gets stuck in that section. And then same thing here. As it heads to the right, it wants to cross that line, but it can't. I don't want to move the graph. But it has to go down through that dot. So it's going to come in this section, and then all of a sudden, it's going to try to keep getting closer and closer. But it's never going to cross it. So that's the middle section. Now, we still have this dot here. We have this dot here. Well, whatever we draw in the lower left is trapped in the lower left. It can't cross those dotted lines. And whatever we put in the upper right, it can't cross it either. But I know as I head further and further left, I'm going to try to get closer and closer to 0. And as I head further and further right, I'm going to try and get closer and closer to 0. So the graph is going to do something kind of like this. As it heads to the right, it gets stopped by a dotted line, and we have a point we know it goes through. As it goes to the left, it doesn't get stopped by a dotted line going left, but it can't go up anymore because it hits that horizontal asymptote. Okay, same thing here. Wants to kind of go down, but all of a sudden it's got to start curving because it can't go through the asymptote. And that's pretty much what these graphs look like. All right, let's hit graph and See how we did. Okay, not bad. I mean, it's hard to get the exact curvature. It looks like it's a little flatter in the middle than I drew. That's okay. But we got the basic idea of it. Any questions on that sketch? Okay, let's try another one of those. All right, so I've kind of got it laid out what you want to find first. Your vertical, horizontal. Let's see. So to find the vertical asymptotes, what do I want to do to the denominator first? About Rachel? We do want to find where it's 0, but what would make it easier to do that? Factor it. Now this is a little bit easier factoring because you don't have to do the 2 sets of parentheses. You're just going to pull out a GCF. What's the GCF of 2x squared and 5x? Yeah. Just x. So x times 2x minus 5. And now we can set each factor equal to 0. What would make the first factor 0? What would you have to plug in for x? Yeah,
0.
just 0. So you're going to have a vertical asymptote at 0. And what would make the second factor 0? Yep. 5 halves, or 2.5. Okay, so there's your verticals. I'll sketch them after. Yeah, I'll sketch them after. Horizontals. So to find the horizontal, what do we usually find first? Yep, and behavior model. So I'm just going to add that in right here. And I'll come back to that in a second. If you're wondering, do you ever get 2 horizontal asymptotes? No, only 1. If you have a horizontal. You don't always have a horizontal, that's going to be tomorrow. But for today, you will always have one, and there will only be 1. All right, what's my EBM going to be? What over what? About chart?
It's going to be 3x squared over 2x.
3x squared, can you say it one more time?
Over 2x, or 2x squared.
2x squared, yeah. And what does that reduce to?
3 over 2.
3 over 2. So my end behavior model is 3 over 2, which means as you let x get bigger and bigger in that fraction, the fraction stays 3 over 2. So I'm going to have a horizontal asymptote at 1.5. Now I think we should sketch our asymptotes. All right, so we've got one at 0 and 2.5. All right, so put one at 0, put one at 2.5. So there's 0. There's roughly 2.5. Horizontal is at 1.5. All right, so let's put that right about there. Okay, so now we just have to figure out what's going on inside there. So the intercepts will help with that, and then the table on the calculator will also help. Let's start with the y-intercept. So the y-intercept is when you plug in 0 for x. What happens if you plug in 0 for x in that formula? About what you would get. Fill in 0 for x. Blake?
It's going to be a 0 on the bottom.
It would be a 0 on the bottom, which means what? Can't do it, which means what's our x-intercept? Or I'm sorry, y-intercept. No. If it was 1, you would have gotten 1 in the calculation. But he said you can't do it, so yeah.
Would it be a hole?
Oh, okay, a hole. I thought you meant, yeah. It's not going to be a hole because there isn't a common factor between the top and the bottom. 2x minus 5 and x would not divide evenly into the numerator. So we're going to get an asymptote. We know that. But what does that mean our intercept would be? Yeah. There isn't one. This graph will never cross the y-axis. Ever. So y-intercept doesn't apply. X-intercept, well, I think it's going to cross the x-axis somewhere. For this one, I'm not as concerned about it because you'd have to basically set that equal to 0 and solve it. I'm not sure that's going to factor nicely. Let me try it quick and see. If it does, then great. If it doesn't, I'm not concerned about using quadratic formula. So 3x and x. If we tried a 1 and a 4, and it would have to be a plus and a minus. So let's try plus and minus and see if that works. So that's 3x squared minus 3x plus 4x minus 3 plus 4 is plus 1. So yeah, the top does factor. So that means I'm going to have 2 intercepts. It's going to cross this axis, the y-axis, twice. All right, so let's see how that's going to look. It's going to cross when x is 1. So x-intercept, x equals 1. If you want to write it as a coordinate, 1, 0. And it's also going to be at negative 4/3. So those have got to be in different sections of asymptotes. Let's take a look. 1, 0 is in the middle section, and negative 4/3, it's like negative 1.3. That's about right there. So now we'll just check what happens on each side of the asymptotes, and that'll give us our graph. All right, so we'll type it in. So we've got 3x squared. I keep losing the problem. Can someone tell me what the rest was? 3x squared
Plus x minus 4.
plus x minus 4. Thank you. And divided by
2x squared minus 5x.
2x squared minus 5x. All right. Sometimes what I like to do is just type in the values I know don't work, just to make sure I get errors, because 0 and 5/2 should give us an error. Yep. And yeah, okay, so that's good. So let's check just to the left of 0. Negative 0.0001. Negative 800, it's way down. So when you're left of 0, way down there. When you go to the right of 0, way up high. So 800. So way up. Okay, let's do 2.5. What's a number that's just a little smaller than 2.5? Wait. 2.49. Sure. 2.49. And you're at negative 300. So when you're at 2.49, it's way down on the graph. Way down there. Okay. And then a number just a little bigger than 2.5? Yeah.
0.51.
2.51. Way up. So positive 300. Okay. And I know that as I head to the right, I'm going to get closer and closer to the horizontal without ever crossing it. And as I head to the left, closer and closer without ever crossing it. So it's going to look pretty much like the last one. It's going to come along. Wants to keep heading right, but it's coming into that vertical asymptote, so it's got to start curving to stay inside that section. So it curves down and just keeps going. All So that's that section. Middle section, it's going to come down. It's got to go through that point in the middle. And then just keep getting closer and closer to that other asymptote. So this one doesn't look like it has much of a flat part in the middle at all. We'll see how well I sketch that when we check it on the calculator. And then here, staying very close, starting to curve away, and getting closer and closer there. Okay, let's take a look and see how we did. There's the section on the left. Okay, notice, yeah, what happens is this one's getting so steep because there's not much of a flat section at all. It almost can't even, well, it's not that it can't draw it. Okay, it shouldn't stop right there. Okay, if I kind of fix it so it looks right, this part should keep going up, and this part should keep going down. But that's pretty much what we sketched. If you wanted to see it, you could take the asymptotes out after. I just leave them. Especially if you're drawing by hand, even if you're doing it on the computer, it's kind of a pain to get rid of them without messing everything else up. Okay, that's how you sketch rational functions. Any questions on that? Alright, so this one I don't want to go through and sketch because it's pretty much exactly like this one. But just for the horizontal asymptote, is it going to be at 0? Or is it going to be a number that's not 0? We did one of each. If you look at that one, which case is it going to be? Horizontal asymptote at 0? Or a number that's not 0? Yeah?
0.
How come?
Because the one in the bottom is bigger.
Yep. Because the exponent in the bottom is bigger, your end behavior model is going to have a variable in the bottom, which means it approaches 0. It's only when the exponents are equal you get one that's not 0. Okay, so homework tonight on 234, 1 through 7. Actually, I guess I could have just done 1 through 9. Odd. I don't know why I did it that way. And then 9 through 12, 15, 17 to 22, 23 to 26, 29, and 33. Those are not all graphing questions. There is some graphing. I usually photocopy like some graph paper, so I have it. I forgot to do that. Would anybody want graphing paper? You could come back and get it after if you wanted. Yeah?
So you need to graph on the homework though?
Yeah, there is some graphing. Anybody want graph paper? Yeah? Okay, I'll make some copies because you'll need it tomorrow. If you want to come pick it up 9th period, I'll just put it on the front table.